Welcome to this explainer. Today, we're diving straight into the highly technical Bombardier Q400 electrical power generation and distribution system. And hey, we're relying entirely on the cold hard facts straight from the aircraft operations manual. So, whether you're an aviation pro or just somebody fascinated by complex aircraft architecture, you are definitely in the right place. Let's get right into it.
So here's our flight plan for this session. First, the Q400 electrical system as a whole. Then we'll break down DC power and batteries, move into AC power generation, tackle system faults and emergencies, and finally wrap up with engine starting sequences. We're using a top-down approach, starting with the macro architecture and flowing right into practical panel procedures. All right, Section 1, the Q400 electrical system. Let's start with the overarching system that supplies basically all of our onboard electrical equipment. We're talking about the EPGDS, which stands for Electrical Power Generation and Distribution System. This is literally the foundation of the Q400's energy. It's got both direct current and alternating current generating systems. Now, it doesn't just passively sit there holding power. It actively manages energy conversion, distribution, storage, control, protection, monitoring, and it provides vital indications to the flight crew. Basically, it controls the whole shebang, from basic battery storage all the way to the readouts on your screens.
And you've got to notice the brilliant separation of duties in the Q400's brain here. The Electrical Power Control Unit, or EPCU, acts as the central intelligence for routing power. It automatically reconfigures the system by opening and closing bus tie contactors if a power source fails. Meanwhile, the GCUs, the generator control units, are the dedicated managers that directly monitor, control, and protect the individual generators. It's like a perfectly choreographed dance.
Moving on to Section 2, DC power and batteries. Let's break down the direct current side of the aircraft. The Q400 utilizes 4 separate types of DC power sources to feed the bus system. We've got 3 24-volt NiCad batteries, 2 engine-driven starter/generators, 2 transformer rectifier units, or TRUs, and an optional APU generator. Now, power flows through the aircraft strictly by priority. The system prioritizes the battery bus and the left and right essential buses absolutely above all else. After that come the main buses, and finally, priority 4 goes to the secondary buses.
Now, this strict hierarchy builds some incredible fault tolerance. For instance, look at the TRUs. You have 2 of these transformer rectifier units in the nose, and they convert 115-volt AC power into 28-volt nominal DC power at 300 amps maximum. Get this, just these 2 TRUs alone can sustain the entire DC system if needed. On the flip side, the 2 engine-driven generators supply 28.5 volts DC and a massive 400 amps maximum once the engine speed exceeds 50% NH. Here is a really surprising but absolutely vital fact straight from the manual. Prior to dispatch, your battery temperature must be at least minus 20 degrees Celsius. But, interestingly enough, there's actually no battery temperature limitation for actually starting the engines or the APU. Kind of wild, right? Okay, let's dive into reading the multi-function display, or MFD. The exact plus or minus decimal readout explicitly tells you the percentage of battery overcharge or discharge. So a positive 1.30, that means an overcharge at 30% over the maximum rate. A plain 0.60 means charging at 60%, and a negative 0.30 indicates discharging at 30% over the maximum rate. Now pay close attention to the safety cues through the color coding. White digits mean you're normal, yellow means the temperature is climbing between positive 50 and 65 degrees Celsius, and red digits warn you it has critically exceeded 65 degrees. So, we've thoroughly covered DC power. But what about the heavy lifters? What powers the massive de-icing heaters and the standby hydraulic pumps? Because the Q400 definitely needs something much heavier for its biggest loads. That brings us right into Section 3, AC power generation. Let's look at the alternating current side of the system. The Q400 is equipped with 2 115-volt AC generators mounted right on the propeller reduction gearbox. They supply variable frequency AC power anywhere between 340 and 560 Hz. But to get that power, your condition levers must be out of start and feather. They need to be in the min to max range. The major takeaway here is that while a single AC generator can handle almost all the aircraft's AC needs, except for the galley bus, which just gets shed, the system logic strictly prevents them from ever operating in parallel. No exceptions. We know the system is robust, but it begs the question, what happens to the Q400 when multiple power sources fail simultaneously? Let's shift our focus to how the EPCU handles critical compound component loss. Section 4,
System faults and emergencies. The EPCU's fault-tolerant operation is brilliantly designed to make sure you complete the mission with minimal headaches for the flight crew. During normal ops, the EPCU is busy controlling 4 bus tie contactors, making sure all DC buses operate perfectly even if you lose up to 2 power sources. But emergency mode, that triggers some extreme vital logic. If you're in the air and you lose both DC generators and at least 1 TRU, the EPCU physically disconnects the batteries from the main buses. It completely isolates them to preserve all remaining energy solely for the essential buses. This ensures your flight safety equipment stays alive for at least 30 minutes.
All right, bringing it all together in Section 5, engine starting sequences. Now we're going to apply these systems directly to the precise sequences used to wake up the Q400.
There are 4 main engine starting modes, starting from batteries, generator-assisted starting, starting from DC external power, and APU-assisted starting. Let's walk through them. First, picture a cross-section of the lower left nose compartment, where the main and auxiliary 24-volt batteries are glowing as they send power to the starter. When starting from batteries, only those main and aux batteries operate in parallel. The standby battery actually sits out to protect the essential buses. A great way to remember this is MAS, main and aux start, while standby sits out. Next, imagine the right engine is already running. The DC generator control unit applies a limit to the right starter/generator as power flows over to the left engine. This is generator-assisted starting. The operating generator helps out, but the GCU strictly limits its current for exactly 15 seconds to protect the loads. Think of it as 15 seconds of fame for that operating generator. Third, picture a ground power unit connected to the left side forward fuselage, with a big red X over the engine generators. That's because when DC external power feeds the airplane to start the engines, the EPCU totally inhibits the engine generators from connecting. The memory aid here is GPU keeps gens in the dark. Finally, if you have an APU installed in the tail cone, its starter/generator connects to the right main feeder bus to supply power in parallel with the nose batteries. Just remember tail to nose. The tail APU pushes power all the way forward to help the nose batteries. Okay, let's look at the exact before start sequence. Step 1. On the DC control panel, switch the battery master lever from off to on. This closes 3 contactors, hardwiring all batteries directly to the essential buses, completely independent of the EPCU. Remember, master first. Nothing flows without the master connecting those essentials. Step 2. Flip the main bat switch to on. On your MFD electrical page, you'd see the main battery connecting to the right main feeder bus. To remember this, think MR for Mr. Main Right. Step 3. Aux bat switch to on. This tells the EPCU to connect the auxiliary battery to the left main bus. Just think AL for AL aux left. Step 4. STV bat switch to on. This connects the standby battery to the left main bus too, right alongside the aux battery, assuming there are no bus faults. So, standby by the aux. Step 5. Flip the Gen 1 and Gen 2 switches to on. This readies the GCUs, permitting the generators to supply power only once the engines spool past 50% and H. Your memory trick? Gens wait for 50. And finally, step 6, manually toggle the main bus tie switch to the tie position. This locks the left and right main feeder buses together, ensuring they share power before the massive draw of an engine start. Just remember to tie the knot before you start.
Now for the actual engine start initiation. It's a simple 2-step process on the engine start control panel. First, you turn the select switch to choose your specific engine position. You're telling the system exactly where to route the starting power. Remember, select to direct. Then, the moment of truth, you physically press the start button. Depressing that button officially commits the aircraft to the starting sequence. Just push for power.
So, you now understand the complete foundation of the Bombardier Q400's electrical system, from the strict bus priorities down to the exact starting sequence. But I want to leave you with a final thought to mull over. Given the immense automated intelligence of the EPGDS when it comes to isolating faults and shedding loads, how reliant should we be on that automated logic versus manual pilot intervention during a truly critical electrical crisis? Are manual overrides becoming a thing of the past? Or are they the ultimate failsafe? It's something every aviator really needs to consider. Thank you so much for joining me on this explainer, and keep learning.